So let's start. So today we'll discuss one very important result in tree that's called matrix tree theorem. This is again it's a it's a seminal result, and surprisingly, this theorem was proved by Kirchhoff's. Uh, Kirchhoff. What is the spelling? Anybody remembers from physics? What is the spelling of Kirchhoff?
Sir, Kirchhoff.
CHOF. Right. So this is amazing that this theorem was first proved by Kirchhoff, who was a physicist or electrical engineer, whatever. And he also proved many important theorem in algebra or the intersection of algebra, graph theory, and analysis. So this is one of these classic results. Historically, this theorem has many proofs. I think at least 6 to 7 proofs are known for this theorem. Some proofs involves more graph theory, some proofs involve more linear algebra, and so on. So we'll discuss a proof that will be almost like an algebraic proof, because we really want to lift that ideas that we discussed during Kelly's theorem to a more general setting, which is the matrix tree theorem. A little bit of linear algebra we'll need. I guess this much linear algebra all of you know, and we'll write down the main points. So it should be self-contained. Okay, so before stating the theorem, let's discuss a few examples. So let's look at 8 vertex. This is a set, and right. And I tell you that you make this set I equal to, let's say, 2, 8, 4 as roots, and construct forest such that the set, I have not stated yet the theorem, I'm just giving you some background. Construct forest such that the set I is the root of the trees in the forest. What I mean by that, for example, like one forest could be the following: like 5, 6, 2, 3, and 1, 8, 7, and 4. So this is a forest. And see, the roots are 2, 8, and 4. And we'll follow a specific direction, since we are thinking like 2 is like the rooted tree at the 2, or 8 is the rooted tree at the root 8. We'll orient these edges. That means from the leaf, we'll orient the edges towards the root. That means from 5 to 6, I put an orientation. So from 5 to 6, I put an orientation. From 6 to 2, I put an orientation. From 3 to 2, there is an orientation. Similarly, from 1 to 8, 7 to 8. Okay. So of course, in general, the vertex set is 1 to n. And we will also use the variables xij. ij running over n. And what is the meaning of these variables? These variables, I'll explain. These variables will be age variables. What I mean by that, see, look at the first tree. So there is an age from 5 to 6. Okay. So this age, I will, oh, why it is happening like that? I don't know. Whenever I'm touching it with different color, it is disappearing. So this age I will label by x56. The 6 to age I will label by x62. This I label by x32. This I label by x18. And this I label by x78. That means the labeling interpretation is that if there is an age from I to j, I label this age by the variable xi. Is this clear? The labeling information?
Yes, sir.
Okay. And with this forest, with the forest, if associate a monomial that I call as xf. What is so when I mean by xf, basically I mean like a multivariate monomial. It is not only one variable. I'm just using the shorthand. For example, the xf that you use for this forest is simply this x56 x, just indicating the ages. 4 is isolated, so there is no age, so you won't care for that. Now, notice that if I tell you the root set, which is in our case 284, and if I provide you the monomial, this gives the full information. Looking at the monomial, you can draw the forest, right? Clear. Likewise, for any forest, you can generate or you can rather associate one such monomial. Okay. So now the generating function that we will be interested in.
Sir, do we separately need the set of roots, or
What
will the monomial itself specify it?
Yeah, in fact, from yes, monomial itself will give you the roots. Yes, because
Okay.
you can direct, right? Yeah. So it's a one-to-one correspondence, right? So the generating function that we will be interested, I'll write it like if n I. So how shall we read it? N is for the number of vertices. In our case, it was just 8, and I is the set of roots. Okay. So this is equal to summation over all such possible monomials, such that f is running over the forest, such that the root of f, which is a set, that's the root of all the trees in the forest, that's equal to I. So this is the mathematical object that I will be interested in. So this is purely algebraic. From graph theory, I have constructed a polynomial basically, which is completely algebraic. And right. And I will be also interested in the following matrix. So this matrix is as follows. So let's draw this will be like n cross n matrix. So let's draw the first. You should think of this matrix is labeled by 1 to, the rows are labeled by 1 to n, and columns are also labeled by 1 to n. The 1 entry of the matrix is x. Yeah, it's difficult to write. I think I should have drawn a bigger picture. It's x11. Maybe I should draw a bigger picture. So I'm not writing that index thing again. I'm writing it like a rectangular matrix, but actually it's a square matrix because the space constraint, I'm not able to write it properly. It's a bit difficult to write here like this. Can you see it all, or this middle line is making some visual problem? Is it visible properly? I have just broken it into two parts so that I can write it.
Yes, sir.
So, okay, so that 1 entry I write it like this, and 1 to 8th entry I write x minus 1 2, then x minus 1 3, and then minus x 1, and the 2 entries x 1, 2 entries x 1 plus x 3 plus x2. Just add everything except 2. And similarly, keep on defining x minus 2n. And you continue this matrix. The last row is x minus n1 minus x n2 minus x n minus 1. And then you have a sum. X n1 up to x n minus 1. So, right? So the diagonals are, if you are looking at the ith diagonals, it is the all the xij variables. So the diagonal ith entry is the summation of xij, these variables. And off diagonal entries minus xij. So this is the very simple matrix. Is the description of the matrix is clear? This is the n cross n matrix. This is a symbolic matrix which
So
has
why didn't you include x22 in the second sum?
x.
I mean, in the second diagonal entry.
This is the diagonal entry.
Yes, sir. So x.
Sorry. This will be x1 to x13. Sorry, I just by mistake.
Oh, okay, sir. So for I not equal to
Because
j,
there is no
in the
loop,
sum.
right? There is no loop. I am interested in trees.
Okay, okay.
So actually, this picture is becoming like this. Good. So this is the diagonal. I hope it's clear. So now, what is the theorem that Kirchhoff's proved? So remember two things. We have got a generating function by the description from the forest, and we have this very interesting looking matrix whose diagonals are kind of sum, and off diagonal entries looks like minus xij. So the theorem that Kirchhoff's proved is that this generating function f ni x, which I wrote here, I should write it like x because it's a function of x variables. This x is equal to determinant of this matrix following Kirchhoff's notation. I'll write it mn. Just give a subscript. Mni. What is mni? So MNI is the determinant obtained determinant of the matrix obtained from Mn by deleting the rows and the columns corresponding to I. What do I mean by that? Suppose, for example, example, let's say I equal to 1 and these two are your roots. Then what you will do, you will take this matrix and remove the first row and the second row and the first column and the second column. The matrix you get, that will be the matrix MNI. It's clear?
Yes, sir.
Okay. Now, I don't know whether you know this explicit expansion for determinant. Suppose you want to write the determinant of this following matrix: y11, y1n. These properties of determinants are already taught in some other course in algebra.
Yeah, last semester in algebra 1.
Okay. So this n cross n determinant has a nice formula which is due to Laplace. This is equal to summation over. Do anybody knows this formula? The expansion formula of the determinant? Have you heard of this Laplace expansion formula of determinant in the algebra class?
I think so, sir, but not by this name.
Okay.
Yeah.
Yeah, so I'll just write that. So sigma is a permutation running over the, I guess this, the basics of permutation groups are already introduced, right? The definition of permutation group, all these things are introduced. The group of permutation, that set of permutation construct a group under permutation operations, composition. These things are already introduced, I guess, right?
So the definition was introduced.
Sorry, definition?
Definition.
So I can assume that you know what is a permutation group, right? Symmetric group, you know.
Yes.
Okay, so good. So the sigma belong to the symmetric group Sn, and the sign of sigma. This, for this class, it is not very important what is the sign of a permutation. It is probably you already know. It's the parity, like the parity of number of inversions of a permutation, which is either +1 or -1, which is not very important for us. So y1 sigma 1, y2 sigma 2, yn sigma. Basically, sigma is a permutation that takes 1 to sigma 1, 2 to sigma 2, and n to sigma n. And these permutations defines the monomials of the determinant. You can easily verify by taking like a 2 cross 2 determinant that this is same. This is known as Laplace expansion formula. So that means if I tell you a symbolic matrix which has kind of variables and its mixture, when I write the determinant of MNI, what I mean is that you expand it using this Laplace expansion formula. Of course, for me, yi's are not pure variables. They are like either they are sum of variables or some negation of some variables. But whatever be the value, it's an identity. So you can plug those things here and get an expanded formulas for the determinant. Any doubt? Or is it clear? Anybody has any doubt? Ask. Yeah, it was important to tell, otherwise one may confuse that what do I mean by the determinant of m and I when I am using the symbolic variables. That is what I mean. Okay, so let's do a few examples. So remember that I want to prove if nix equal to determinant of, technically I should write it like x because this is also symbolic determinant. Okay, so let's take a few examples. Some really simple examples. Let's take I to be empty set. No vertex is designated as root. That means there is no forest, right? So that if in empty x must be 0, there is nothing root, so you cannot have anything in the forest. Now look at this determinant. If I equal to empty set, then you no need to remove any row and column from the determinant, right? Because that's the definition, because I is empty set. So what is the determinant of mn? Look at it, it's a very interesting determinant. Let me write once again, then you will be able to understand. So this is x11 up to x1n minus x12 minus x1n minus x21 x21 plus x2n minus x2 minus xn1 minus xn2 minus xn1 plus xn into n minus 1. So what is the determinant of it?
That is 0.
Yes, why is that?
So we add all of the columns to the first column, and
That's right.
oh, yeah, they all become 0. Yeah, sorry.
Yeah. So, right. Because I am doing an elementary operation, I am not changing the value of the determinant. As he said, columns 2 to n to the first one. So this determinant, this matrix has a very nice symmetry. Okay, so this was example 1. Let's take an example 2.
So this is one small
Yes.
thing.
Sorry?
So in your matrix, your last element, you're taking x of n comma n minus 1. Why not n comma n?
Sorry, this is 1, 2. Sorry, I made the same. This is starting from 1, 2. Yeah, what was your question?
You're saying in that matrix that you wrote, the last element on the bottom right, you took x n comma n minus 1.
Right.
So why not n comma n? Oh, actually, you took
Because I am interested about the trees. So there is no loop.
yes.
So this, I mean, the intuition is that these variables will be ultimately my tree variables. That's why I am not interested that xii kind of variable.
Yes, okay.
Okay. So example 2, let's take I to be something interesting. Maybe I just n. Okay. So what is if in x?
So we remove the nth row and column, so it's the top left submatrix.
Right. And so that means the determinant of m in n, you will remove this row and this column, right? Now, what will happen to that left hand side and right hand side, this equality? Okay, maybe this case is little bit difficult at the moment. Let's not discuss this case. Let's take an easier case. Sorry, this is slightly. I wanted to give example of few easier case. So let's take that I equal to 1 to n minus 1. That's an easier case. So if I equal to 1 to n minus 1, these are all the roots, right? Then what is the generating function of f I n x? Because they are all like roots, right? 1, 2, up to n minus 1. Now this x, that nth vertex will come, and either it will go with this, or it will go with this, or it will go with this, right? So what is the generating function for it?
xn comma 1 plus xn comma
Right,
2.
xn1 plus xn2 plus xn n minus 1. Now look at this matrix. You have to delete first n minus 1 rows and first n minus 1 column. So what remains is that this 1 cross 1, this entry. Same as determinant of. So you verified some very simple cases. Okay. So let's just work out another final example. So it's slightly more non-trivial, or rather more interesting. Example 3. Let's take n equal to 3. So the vertex set is 1, 2, 3. And my I is just 3. Okay. So what are the different trees in the forest that is possible? Or rather, the different spanning trees. So one possibility could be 1, edge goes to 2, edge goes to 3. And then other could be 2 goes to 1, goes to 3. 3 is always the root. So I'm drawing like that. And the last possibility is the 1 will go to 3 and 2 also will go to 3. Now let's draw the matrix form of it. So what is n3? Let's draw it carefully. x12 plus x13 minus x12 minus x13. x21, x22 plus x23 minus x23. x31, x31 plus x32. Now let's remove the third row and third column.
Sir, it should be x21 plus x23.
Yeah, so I'll just do that explicit computation and show you that what Kirchhoff's theorem promises is correct.
No, sir, I mean the second diagonal entry.
Second, it's 2, 1, 2, 3. So this will be x12, x21, x12, x23 plus x13, x21 plus x13, x23 minus x12, x21. So this will cancel. So this will be exactly the thing. And from here you will get it x12, x23 plus x21 x13 plus x13 x23. Yeah. So we got exactly what we want. Oh, we got something wrong, right? Where did it go wrong? x12 x21 x12 x23 minus x1 somewhere I made a mistake. X13 x21 x13 x23 x12 x23, this term is there. x13, why did I write it? Something's wrong. x13 x23. No, it's correct, right? Yeah. Same. Yeah. So that
So
as
it's right. So
yeah, so it's correct. Here it has to be. So this is the few examples like to convince us that this theorem is plausible. Okay, so let's try to prove that. How do you prove it? So again, we'll use some induction idea. Before we prove that induction things, let's make a few observations just like we made in the Kelly's theorem. So in the left hand side, when you look at this term f in ix, each monomial has at least one j such that all xij variables are missing. Why is that? Because it's a forest, right? So it will have some leaf. And if some j is a leaf, then there is nothing that comes inside j. Everything will be going upward from j. So there is no variable like xij. It's obvious. This is true even in the right hand side. Why is that? Because if you look at determinant of mn I, so you have deleted that ith row and rows and columns inside the set I, right? So the dimension of the matrix is n minus I. Of course, I am working on something non-trivial, like not a vacuous condition that I equal to n, which is like trivial. Then if every j has some variable xij, then the degree of the terms in the right hand side will be at least n, right? So
Yes,
so the determinant of mn I is a homogeneous polynomial. Homogeneous means every term has same degree of degree equal to n minus I. So it cannot be the case be the case that for all j some xij variables presents, then the degree has to be n. That means that both the side will be some kind of leaf type variable. One side is obvious, left hand side. The right hand side also is a degree argument, and this is true. So this observation will be useful, and using this observation, we'll use this observation in the induction, right? Now, without loss of generality, it's symmetric. So without loss of generality, assume that j I will work is simply n, just to make my life simple. So that means if we substitute, this is another observation, observation 2. If we substitute x xin variables to 0 in LHS and RHS, what do we get? From each side, we get terms that do not, is obvious thing I'm writing, involves the age variables xin for any I. That means the n is playing the role of the leaf in the both side. Is clear? Observation 3. If for every such j, like in our case, j equal to n in this case, it's a special case. We prove that Pj of LHS is equal to Pj of RHS, then we are done. What is P of j at LHS? This is equal to Fnix. Substitute xij variables to 0, and here the determinant of Mni, substitute xij equal to 0. So this is Pj of RHS. It's naturally defined. That means I want to prove that these two polynomials are equal, right? Instead of proving that directly, I will use this strategy. Okay, so I fix some j. I will show the correctness for only one j. Other j's are symmetric argument, same argument essentially. So I fix some j, which is j equal to 1. What I'm interested to look at all the monomials in the left hand side that do not involve any age variables xin type. So right, how do I get it? If I plug xin equal to 0, then the monomials which are not interested with, they will disappear. And that polynomial is my polynomial fj LHS. Similarly, I obtained the polynomial fj RHS by plugging that xij or xin variables to 0 to the right hand side. I will compare these two polynomial and prove it to you that this is same. And if I can do that for all j, then I am done. Why is that? Can somebody say? This is like this Kelly's theorem type idea. So do you follow that? What is my strategy of proving that these two, ultimately what is my aim? My aim is to prove this theorem that says these two polynomials are same. This is my goal, right? To prove these two polynomials same, we are trying to fix a strategy. So what is the strategy? The strategy is, it is enough to prove that for every j, this pj LHS and pj RHS are same. I'll show you the proof for only a special choice of j, that is n. Proof for any other j is symmetric, same. But why it is enough?
So because this lets us compare certain coefficients, and by subbing each of the xi raised to 0, we get to compare all coefficients.
Very good. So because if you know that every term will have at least one such leafy variable, right? There is no h, both in the left hand side and right hand side. And suppose some monomial, as he said, Gautam said, some monomial has different coefficient. Then we know that the leafy variable, if j there, then I know that pj LHS has to be different than pj RHS, but I already have proved that they are equal. So this is enough.
So can you repeat this part also?
Yeah. So let me just write a couple of lines, then it will be more clear. So the claim is that then we are done, right? And the answer that you are trying to justify, why? So when you say that, so if nix, this polynomial is not same as determinant of m nix, how can the two polynomial are not same? Definitely there is some monomial, that means there exists some monomial m such that the coefficient of m in this notation is used in math always, like coef m means coefficient of m in f nix bar is different from the coefficient of m in determinant of m and ix. Then only these two polynomials are different, right? There has to be at least one monomial which is different coefficient. It could be zero some cases, but they has to be different. But by our observation, m has a leafy variable. This is not a mathematical term, just to give the insight I am defining. Leafy variable j. But we already have shown proof that pj LHS is equal to pj RHS. So who asked that? Why it is to explain? I did not look at who asked.
I think
Ramit. Is it clear, Ramit, now?
yes, I think so.
Because if the coefficient, we see this coefficient m rests in these two polynomial, right? pj LHS and pj RHS. Because that's the leafy part that comes out after substituting x ij variables to 0. Now, if some monomial has already a different coefficient, then these two polynomial cannot be same. Right. This beauty of this proof is that they are not very involved, but there are lots of small pieces, and you have to kind of stitch them together in a consistent way, and then the nice picture comes out. So, right now, with after all this observation, we are kind of ready to induct. 1 minute. Just Yes.
Sir, could you repeat the proof of the first observation again?
1 minute. Let me just go back.
For the right hand side.
You mean this one?
Yes, sir.
Yeah. So the what? So you want to go over the proof again?
Yes, sir. For the right hand side, I didn't get why the degree prevents us from having all of the xij's.
Oh, because the what is the dimension of the matrix for which you are computing determinant? That is n minus the cardinality of I, right?
Yes, sir.
So if you take a determinant of a n minus I cross n minus I matrix, then
Yes,
the
sir.
determinant polynomial will be a homogeneous polynomial of degree n minus I.
Yes, sir.
But for every j in n, if you have some variable xij present, then the degree cannot be n minus I, it will be at least n.
Sir, could they not be present in different terms?
But they are homogeneous. So if there is any term that is like violating this property, then that term will be of degree n. But this is a homogeneous polynomial. All terms are of same degree.
Right. Okay, sir. I think I misunderstood the statement. The statement is that for any term, there is some ij which is missing.
Right. I did not
Okay,
write
okay.
it completely formal way, just to, because that will make it very tedious in this online way writing. So
Right,
notice
sorry,
that
sir.
homogeneous. No, fine.
Okay.
No, it's
Got it,
good
sir.
to
Thank
ask
you.
question. Yeah, good to ask question.
Thank you, sir.
Yeah, you're welcome. So okay, so let's now try to do the induction. So we'll assume the truth. So remember that I am going to prove this equality. Okay, so there are two things can happen. So we focus on only j equal to n. Any other things are symmetric. So the case one minute, I'll just switch on my light and come back. So case one. So let's say the n does not belong to the set of, so I is the set of roots, remember. So let's say n does not belong to I. Then what will happen? What is fn ix? That means you already have the forest for f n minus 1 ix. So these trees are there in this forest, right? And then this nth guy will come and will get associated to any of these variables present there already. That means that if you think properly, the generating function fn ix will be x, n can be attached to 1, or n can be attached to 2, or n can be attached to n minus 1, And then you have the generating function for n minus 1 ix. Is it true? Everybody followed why I directly jumped and wrote that? True, no? This is because if every term of f n minus 1 ix is like a monomial for a forest, right? And this forest will have variables 1 to n minus 1. And this guy n will come and it will get associated to either 1 or 2 or n minus 1. And use the age variables either xn1 or xn2, xn n minus 1. Agree? Or anybody has any doubt?
Sir, but then no element
Yeah.
will have n as its parent, right?
No element.
Like no element will be connected to n like, as its parent.
No, 1 minute. No, you are saying no element will be connected n as a parent.
Yeah.
No, because remember that what I am trying to do, I am trying to extract the things that does not have this kind of variable xin,
Okay. Sir.
because I want to prove that pj LHS equal to pj RHS. So for me the j equal to n. So I killed those possibilities. It's a good point, but I killed those possibilities because I don't want any such edge that goes to I to n.
Okay. Sir.
Is it clear now?
Yeah.
It's a good point. And now look at the right hand side. So right hand side, what will be the case? So I have this very nice matrix Mn, and n does not belong to the I. So basically that means I don't delete this nth row and nth column. So my I set is somewhere here. In particular, I have this point intact. xn1 plus xn2 plus xn minus 1. And these rows are also intact. Right? Maybe I should draw a bigger matrix. It's getting too small. Here the blackboard is very useful. Unfortunately, we don't have it. So remember that my matrix shape is x11 plus x12 plus x1n, and then minus x12, and sorry, again I wrote the mistake, x1, 2, and 3. And what was the final entry? That is minus x1n. And remember that all my xin are 0. So this entry is 0. Similarly, minus x21, x23 plus x2n, dot dot dot, and this term was minus x2n. This is also 0. So this is 0, 0, 0. This everything is 0. And the last row was minus xn1 minus xn2, blah blah blah, xn1 plus xn minus 1. All these columns are 0 because of this property. True? Is it difficult or is it okay? Because I want to zoom to this polynomial. Always remember, I am zooming at the polynomial Pn LHS and Pn RHS. So I am putting all xin variables to 0.
Yes, sir.
Right? Now my I set is somewhere here. So maybe my I set is, this is my I set, this is my I set. So I just delete these rows and these columns indexed by I set. And after I delete, what will happen? So I want to compute this determinant. These things are 0 and these things are, some rows are deleted, not the final row. That means if you look at it carefully, it's very easy to see that the matrix that you are interested will look like the following. It's nice picture. So this entry will be x n1 plus x n2 plus x n minus 1. These entries will be x n1 minus x. I don't know what it will be. It will be something.
So in the diagonal elements also, the two I comma n terms will be 0, right?
Say it again.
Sir, in the diagonal elements, the I comma x
Yeah,
I
yeah,
comma n.
those things will disappear, right?
Yeah.
But here the matrix that you will get is m over n minus 1 and this I set. Whatever I set determines, this will determine the matrix here. Yeah, all these things, you're right. This because the 2n will be 0, for example. So this mni I will be a different kind of matrix. But that does not harm because n has disappeared. I am looking at only over n minus 1.
No, so like in the previous matrix, you haven't deleted that.
But I am now working over n minus 1. So the
Yeah,
diagonal need not to be 2 to n. It should end at 2n minus 1. That is exactly what is happening when you substitute 2x 2n equal to 0. It's a little tricky. Yeah. But what is this determinant? Expand along these rows. So one term will be when you expand along this, and this term will look like x1n plus xn minus 1 times determinant of, sorry, I'm using slightly, and the rest will be what? They are all 0, right? Expand the determinant along the last row. One thing will be corresponding to this corner term. That is basically this term, this determinant. But if you want to expand around these terms, what will be the effect? You have to pick up the 0. Is it true? Because there is no choice. Anything you take from here, this you have to take something from here, and that will be 0. Not clear.
It's clear, sir.
Clear? Okay, good. So that means these additional terms are all 0. But this is now you can use induction hypothesis. Inductively, you know that this term is equal to your f n minus 1 I x. Same thing we got. So in this special case, it is easy, right? Case 1. And what is case 2? Case 2 is n belong to the root. It is actually even beautiful. So if n belongs to I, that means n is a root vertex, right? And also we have substituted these variables xi n equal to 0. These things are not there. So n has become like an isolated vertex. Because any incoming edge variables we have kind of deleted. So what is the forest generating function? If you look at carefully, every term of this forest, so take this new set J, which is like I minus N. This is just the forest over N minus 1 variables whose root set is J, because N is removed. So this is equal to basically F N minus 1 Jx. Why is that? Just, I mean, it is clear, but let's go back to the first examples. See, when this 4 was isolated, we do not count that 4 in the monomial, right? This monomial was just a forest over other N minus 1 variables.
Yes, sir.
And the determinant side, what will happen? Now you have deleted that nth row and nth column. It is exactly what you get is this determinant, which is like m n minus 1 jx. So it is equal to determinant of m n minus 1 jx. That's it. That's the proof. So we have proved that Pj LHS is equal to Pj RHS. It's little tricky, but it's almost like self-contained. We do not require any. There are some proofs of this theorem that uses little more linear algebra, but here we almost avoided any amount of linear algebra except the determinant computation.
For all J, the argument is the same, right?
Same, yeah. Because there is never I have used anything particular about J equal to N. It's
Okay.
yeah. Now let's look at one interesting corollary. Derive Kelly's theorem out of it. The theorem that we studied last time, right? So what is Kelly's theorem saying? That if you have a complete graph N, the number of trees or like spanning trees is n power n minus 2. So now how will you derive this from the this theorem that we just discussed? For every spanning tree, you can think of like it is rooted at n by putting the orientation properly, right? The way we have oriented, you can always make like n as the root and orient the edges like that. So we'll fix my I set to be just n. It's without loss of generality, you can work with anything else. But I know from this theorem that if n x is the determinant of this matrix. I'm not writing it again and again. But I want to count now how many such spanning tree. That is the Kelly's theorem. So for counting, what shall I do? I know an expression for this. And for the counting,
We could substitute everything equal to 1.
exactly, for the counting, this is a beauty of this algebraic technique. For counting, xij equal to 1 for all ij. So if you put that, then just inspect the determinant. Then the determinant that we have to work out, symbolically what was there? This is x12 plus x1 n minus 1, and I'm not writing again and again. So if you put everything is equal to 1, then the diagonal entry will be n minus 1, and then it will be minus 1, minus 1, minus 1, then it will be minus 1, n minus 1, minus 1, minus 1, minus 1, minus 1, minus 1, n minus 1. Now, what is the determinant of this nice matrix? So this determinant is equal to determinant of this matrix. So what I will do, I will add all these rows to the first row. There are n minus 2 rows, right? I will add them to the first rows. So what will happen? It will be 1, n minus 1, n minus, all will be 1, right? Because determinant is preserved under that operation. So row 1 is replaced by row 1 plus row 2 plus row n minus 1. So this is n minus 1 cross n minus 1 matrix, because I have deleted that nth row and nth column. But this is same as determinant of 1, 1, 1. Then I will add the first row to each of the rows. 0, n, 0, 0, 0, n. Row j is replaced by row j plus row 1 for all j greater than or equal to. Determinant is preserved under these operations, and but this is equal to
Sir,
n
how
power
did,
n. Yeah.
sir, how did the last element of that become 1? Because n minus 1 is in the nth row.
Which one? 1 minute. Say it again, your question.
Sir, in the determinant, when you did the operation R1 plus R2 plus Rn minus 1, so the in the first row, the last element, how did it become?
First row, the last element, which was
Yes,
minus
sir.
1. Because there is n minus 1 added, and there are n minus too many minus 1.
So, but you did not add the nth row, right?
There is no nth row. It is n minus 1 cross n minus 1 matrix.
Oh, okay, sorry.
Because you have deleted the nth row and nth column, right? Because your I set is n. So you have deleted the nth row and nth column.
Okay, sir, it's clear now.
Okay. So see, this is some very interesting way you get back that Kelly's theorem. Okay, so I don't know, today's lecture I can make PDF and upload easily. How much size it will be? It looks quite big. I have to see.